It's 12, so it's time to start. Let me begin with an announcement. So I'm really happy to announce that we have a new member of our organizing team for this colloquium. It's Dr. Maciek Bielicki, and he will be responsible for all the talks which are connected to astrophysics and cosmology. So if you have a speaker who wants to give a talk in this subject, please contact Maciek, not me, and he will also run those seminars which are in these subjects. So because today we have a talk which is about cosmology, I'm passing the microphone. Maciek.
Okay, thanks. So, as you have heard, about 2 weeks ago, the Nobel Prize in Physics 2019 was given to three people, and it was shared. So one half was given jointly to Michel Mayor and Didier Queloz for the discovery of an exoplanet orbiting a solar-type star. So this is the short description, and the other half was given to James Peebles from Princeton University for theoretical discoveries in physical cosmology. And today, Wojciech Hellwing, member of our Center for Theoretical Physics, will tell us about what led the Nobel Prize Committee probably to award this the most important award in physics to James Peebles. Okay, start.
Thank you very much. I think it's easy to say, or safe to say, good afternoon, ladies and gentlemen. Thank you very much for coming. This talk was prepared relatively in short notice, as most of the physics Nobel Prize talks are, although I need to make one thing clear at the very beginning. I'm not going to give you the explanation that probably, or motivation that was behind the Nobel Prize for the Nobel Committee, because I have no idea what was their motivation. I can only tell you if I would be on the Nobel Committee, these things I'm going to present here for me would convince me already years ago to give Nobel Prize to Jim Peebles. So without further ado, let me start, because it's going to be a very difficult task for me, because the other half of the Nobel Prize is given for nearly physical, something you can really clearly describe and define discovery. There's observation of exosolar planet going around a star that is more or less like our sun. So everyone knows what a planet is, everyone knows what a star is, everyone knows more or less how you can observe things like that. It's one particular discovery that, of course, this was not only just for discovery, but also for implementing, developing, and bringing about a completely breakthrough method for discovering this kind of planets as well, that really changed the picture of the whole field. But this is not the talk this talk is going to be about. But my task is much more challenging, because I fully agree with Jim Peebles that what he said during the press release in Princeton University, that when he was asked a typical question by a journalist, Professor Peebles, what you would consider your greatest accomplishment that this connects with the Nobel Prize? And he said, this is really life's work. And definitely this is really life's work. I will convince you that the physical cosmology would have been probably 20 years behind what we have now without contribution of Jim Peebles. So this quotation is not mine, but I fully agree with this. Is by Sean Carroll, by famous British relativist, that how come around half of the modern cosmology is a footnote to Peebles. And this is a picture of Jim Peebles from 90s. There was a workshop of course, about cosmology. And I really like this picture because I had the pleasure also to meet Jim Peebles in person. He's absolutely charming character and very, very easygoing and very friendly. And usually you will now see all these pictures with him being very well-established professor, but personally he's a very, very warm humankind. So really like this picture that, not everything needs to be really distanced and academic-like. Okay, now please bear with me. And if something wouldn't be clear, please don't hesitate to interrupt me. I hope I only have 20-some slides, so there should be enough time to discuss things with the details. So before I really start expressing and describing the contribution to the field by Jim Peebles, I need to define the field itself. Now it's easy to define, but as you will see, as I will set the stage as it was in the 60s when the story will begin, there was much differently then. So physical cosmology is a, well, I scratch out new because it was a new empirical, very, very new kind of way of thinking about the universe 50 years ago. Now it's fully fledged, empirical, precise field of physical sciences concerning the study of the large-scale structure and dynamics of the universe with the fundamental questions about its origin, structure, evolution, and ultimate fate. So basically, we get some starting point, get some initial conditions, try to use equations and simulations, and to understand physical modeling, basically applying physical modeling to understand the universe. So this field of study, the study of the whole universe and its structure, is rooted in a very one fundamental assumption. And this can be also regarded as one of the weakest points of physical cosmology, but so far, we haven't been able to find at least one convincing argument why this assumption should be abandoned. So basically, the foundation of modern cosmology lies in the laws of physics. So we all know what the laws of physics are, general empirical rules describing natural phenomena based on empirical evidence, very important, and are expressed in language of mathematics. So Newton's law of gravity, Gauss' law of Boyle, quantum mechanics, general relativity, etc. So they need to be tested empirically on Earth because from this theory, we have a control sample, control environment conditions for experimental physics, and then we extrapolate them to the whole universe. So we assume that they are universal. And this assumption is commonly known, and this is the foundation of the modern cosmology, as cosmological or Copernican principle, which can be more or less expressed in the following statement. We state that we are not privileged by any means observer of the universe. This means that global properties we infer about the cosmos are close to the cosmic mean, so close to some idealized mean average observer would infer as well. This is very important because if we would happen to be a very special observer, so for example, the universe wouldn't be homogeneous but we wouldn't know about it, what we would infer about the cosmos wouldn't be really a general property, global property of the cosmos itself, but something related to our special location in space-time. But of course, the universe is not fully homogeneous, otherwise this room would be just full of gas and there would be no observers. So there are scales at which inhomogeneities appears, and this will be a story about this inhomogeneities as well. But in the large scale, grand scale of schemes, we do believe and we do observe that the Copernican principle holds. So once we assume this, we can start thinking about the cosmos in the physical setting. So it all started with the Big Bang, of course. It's not true, but before that was the general relativity by Albert Einstein. And this is really the rudimentary state of physical cosmology. Without GR, there was no possibility of really thinking and building precise model, physical model of the whole universe. Of course, there was Newtonian cosmology before, but many things in Newtonian cosmology were just intuitively understood and brought to not relatively good conclusions. So we have a general relativity to describe the universe at the larger scales. And this is going to be just two slides with some equations that I will torment you with. This is just necessary to understand the background picture, and then we're going to go to much lighter content of the physical cosmology. So basically, once we apply general relativity to the whole cosmos, we need to assume something about the symmetry to reduce the complexity of the problem. And usually, it started with something it's now called as Friedman-Robertson-Walker metric, line element expressed in this way, when this parameter k expresses a free parameter that constrain the global geometry of the space-time. So positive k means the geometry of the hyperspace, vanishing k means the flat Euclidean geometry on the larger scales, and negative k means the geometry of a hypersurface of a saddle. Now, if you vary Einstein-Hilbert action with respect to that metric, you can derive two Friedman equations. One is called acceleration Friedman equation, and the other is just, let's say, the mean Friedman equation. And these solutions were more or less found independently. First, of course, they were coined by Alexander Friedman, but later also developed by Belgian monk Georges Lemaitre. And this is important to notice that if we assume this metric, the Friedman equation in this form, and the only one that admits global solution with universe expanding in a manner that satisfies observed Hubble law. So this is observed Hubble law. So escape velocity of a galaxy is proportional to a distance from which the galaxy is separated from us. So you cannot find other solution with this line element, other equation describing, admitting for such behavior. Okay, so we all know this is textbook knowledge. So just very quickly add another element which allows us to tell something more about the evolution of the universe. So we need to fill the universe with something. At early days, people considered empty universe, like means there was a universe filled only with Cosmology constant. That was the de Sitter universe. There was Einstein de Sitter solution with the universe only filled with matter, and so on and so forth. So basically, in general relativity, you fill this by selecting what are the content of the energy momentum tensor by filling it with the different fluids. We assume the fluids do not interact. This is all, of course, very crude approximation. And then each of these fluids has its own equation of states relating pressure to the energy density with the parameter W. And now we need to assure that there's energy conservation in such a universe. And this can be done by requiring that the zero component of this energy momentum tensor, its covariant derivative actually vanishes. So if we put this, we can obtain the equation of motion relation of the density with respect to time. For each component separately, this W should have been indexed maybe with I. So each component, depending on what equation of state it has, would have a different time evolution with respect to its density. So for example, for a non-relativistic matter, which is called dust in general relativity, this W is equal to 0. So there's a pressureless matter. So here is 0. So the energy density of matter scales with time as A⁻3, which is something natural. If you grow a sphere, its density drops with the cube of its radius, for example. So now we can express the Friedman equation in the following way using all this before. So we have a term with the curvature, term related to the density, cosmological constant, and if we say that these all densities are basically called omegas, and this is how omega is defined. So basically it's a contribution of each of different component, radiation, matter, dark energy, with respect to something we call critical density, which is defined like this. Critical density is the density of the universe that would be having a vanishing global curvature. We can start describing different scenarios. So this is a plot that shows you, depends how you choose your contents of the universe. For the clarity, we've disregard any relativistic component because at late times it really is not important. Like radiation scales with the A⁻⁴. So for example, at early times is very important, but at late times is not. You will see that the universe can be closed. It's well-known textbook from 80s, even 70s and 60s. So after some initial phase of expansion, it would contract. It can be coasting universe, so it's this called open universe, which means it grows, but pace at which the universe expands is asymptotically approximate going to 0. So basically it's slowing down, but will never slow down. It slows down at infinity. For the universe with filling, this is the case for the universe filled with matter equal 1. And then if you have cosmological constant, then you see that the universe expands, and at some point expansion starts to accelerate. But the important thing to notice for all this family of solution, you will see that there was a point back in time in which the radius of the universe was 0. At least, even if not was 0, this was called back then primordial singularity. As we go back in time, we get that the radius of the universe shrinks. This means that the density goes up. So that was an obvious indication that probably there was an area in the evolution of cosmos when cosmos was dense and hot. And this is something that set the stage for us for the whole story. So consequences of the Freedman equation solution is that the universe is dynamical. It either expands or contracts. As a very, very short footnote here is that famous misquotation that Einstein considered lambda his greatest blender is complete misquotation. Einstein never considered introducing lambda as a blender or any mistake because this is just a constant of integration. He considered using lambda to get static solution as his mistake because it was obviously point to him later by Friedman, for example, that as soon as you balance out lambda very critically with the matter content, universe is static, but it's very unstable. So the timeless fluctuation will unset this static solution, and universe will contract or expand. So basically, we cannot get static universe. Universe can only contract or expand in general relativity. So Lemaitre already coined the idea of primal atom in 30s. So the state in which universe was very hot and dense. If it was contracting, it wasn't expanding now, it was much smaller in the past. So early works of this idea involve Gamow and Lifshitz that used Jeans length for galaxy formation. So Jeans, that was another British astrophysicist that considered fragmentation of gas clouds and found out that in expanding universe, there's a critical size of a perturbation in order for perturbation to collapse. Otherwise, if the perturbation is too large, the universe, expansion of the universe would not allow it to collapse at given epoch. So in 1948, Gamow realized that structures cannot form until the density of radiation drops to be comparable to the density of the matter. And that's the same year, Alpher and Hermann suggested that the primal radiation should have currently the temperature around 5 kelvins. And then that set the stage, and then they came 1965, completely sensational year for cosmology. So it's all known, part of the story, that two Nobel Prize winners later, Arnold Penzias and Robert Wilson, who back then worked at Bell Laboratories, discovered now something we call CMB. But before they discovered anything, they actually meet astrophysicists, very young astrophysicists and promising from Princeton, Jim Peebles, who actually discussed with them that the cosmologists expect that there should be a radiation that would look like thermal noise coming from all areas of the sky, because the Penzias and Wilson had no idea. They tried for months, many different ways to get rid of this excess noise in their antenna. And they had no idea, but someone told them, I don't remember, there was another physicist, that there's a group at Princeton, there was Jim Peebles back then, Robert Dick, and Wilkinson working about these ideas, and they met, and only after they met and discussed, Penzias and Wilson decided to publish the finding. And in the same very issue of Astrophysical Journal, there was a preceding article, which I'm going to show you because it's completely amazing, 6 pages, one of the best 6 pages articles I ever read about astrophysics, that actually explain everything to the readers, what the Penzias and Wilson had found. But back then, unfortunately, Nobel Committee weren't so ready yet to give prizes to theoretical discoveries. So only Penzias and Wilson got the Nobel Prize for completely serendipitous discovery. They got the antenna, and they got this. I met someone who explained to them what they actually discovered, and they got Nobel Prize. Well, that would be very nice for us. But fortunately, at least after the years, we can say a little bit justice was given, since now at least Jim Peebles, also for many different contributions, has the Nobel Prize. Okay. What's the story? So Penzias and Wilson detect this unaccountable excess, they called noise, radiation in their horn antenna. That's a picture years later because they were quite younger. And it's estimated to be black body thermal radiation equivalent to 3.5 keV rest frame temperature. And they published this discovery in the Astrophysical Journal. In the same issue, as I said before, Dickey, Peebles, Roll, and Wilkinson published an article explaining what's what. And this is Wilkinson, this is Dickey, this is Jim Peebles, and this is, I think, Edward Groth, but I couldn't find a picture of James Roll, so I'm sorry for him. Apologies to him. And I'm going to give you a few snapshots of the pages, which I don't want to read in the whole details, but will highlight few of the issues. So let us see that this is one of the starting pages of the Dickey and Peebles et al. Article. So they say, They actually say that lately they learned about this discovery of this measurement by Penzias and Wilson, and they say, while we have not yet obtained results with our instrument, because they already were building their own antenna, being so convinced that this radiation needs to be there. We recently learned that Penzias and Wilson of Bell Telephone Laboratories have observed background radiation at 7.3 centimeter wavelength. In attempting to eliminate or account for every contribution to the noise seen at output of their receiver, they ended with a residual of 3.5 plus minus 1 Kelvin. Apparently, this could only be due to radiation of unknown origin entering the antenna. And then they explain this is exactly the radiation you expect if you understand that the general relativity, many different parts already known of the physical cosmology should work. So, now, the crucial contribution in this paper to understanding comes actually from earlier result by James Peebles that is related to the helium abundance, primordial helium abundance, of which I will say a few words in a moment. But let us read a little bit more. So it has been pointed out by one of us, James Peebles, that the observation of the temperature as low as 3.5 kelvins, together with the estimated abundance of helium in the protogalaxy, provides some important evidence on possible cosmologies. This comes about in the following way. And then they describe that how the density of matter at the time when the primordial helium was nucleosynthesized is tightly related to the amount of helium that was produced in the early universe. And this is all in connection related to the temperature you observe now from the radiation that was back then. And this goes the following way. So when the universe was very hot and dense, and of course in thermal equilibrium, you can work out the balance equation about production and destruction of various nuclear components. But for this talk, the most important one is helium. So you start with the production of deuterium, so by colliding one neutron, one proton. And if you start producing enough deuteriums, and then by colliding two nuclei of deuter, you can produce helium-3, and then colliding with another deuterium, you produce helium-4. And this is already much more stable against any destruction nuclei. The thing is that this is the plot from the PBUS 1966. It's also a very interesting story because this paper was submitted a year before it was published. But basically, it was so outgoing in its claims, and that the editor said, I think one of the referees, that basically this cannot be published because there's like some kind of a nonsense. So this paper was eventually published before the Penzance-Wilson discovery, but it already prepared the ground. So people fought for a year to get this result published. And the plot can be described in the following way. So here we have rescaled the axis about temperature, about this residual temperature that you would observe currently at redshift 0 on Earth. And the scale changes depending what would be the total density of matter during the recombination. So sorry, at current epochs, but of course it scales with the time. And this will be helium abundance by mass related to, of course, hydrogen abundance. So basically this is deuterium abundance. You see that this is very sensitive function of the temperature and the density, but also helium abundance, primordial helium abundance, also sensitive function. So for example, if you measure 3 Kelvins radiation, this is what we're more or less expected, and assume this density of matter, you would yield that helium should contribute 30% by mass, the primordial helium. But if the density would be nearly 2.5 times higher, you would yield already smaller by 10% yield. Going even higher. Going to even higher density, you will get much smaller helium yield. So basically, that's why you can use this measured temperature, and if you have information about the density of matter from some other sources, you can predict what should be the yield of helium, or you can turn around. This is really physical cosmological thinking about the universe. It was something very fresh back then to work like that. To take the local observation and think you can really apply this complicated math and physical assumptions to go to early times. So if you measure this, and you can measure this more or less by observing primordial clouds in our galaxy, back then it was already some initial observations, you fix this yield, you can say what should be the density of matter if you know the current temperature of radiation. This is the modern version of this plot with the perfect observations and math and calculation we have. So this is deuterium, lithium, helium-3, and helium abundances. And basically this band is something that is more or less allowed by the current observations, the density of nucleons. Back then they would say density of matter, but we really mean density of the nucleons. So let's go a little bit more with this paper. So they write a little bit later that this result can be used to estimate the density of the universe. But I really like these many phrases in this paper that, for example, assuming that general relativity is valid. So they already back then, they were cautious enough to say things in a really scientific way. So they result hold if the general relativity is valid. And this is 60s we're talking about, but there were completely no strong test of general relativity except the Eddington and some observations of the acceleration on Earth. You can use this result, as I explained you before, to yield the estimated density that should be in order to produce helium and leave this residual temperature. But this is factor of 20 below the estimated average density of the matter in galaxies. This is a little bit by chance, but this is exactly the factor now we know, more or less, is factor of 20, but we know the factor of the densities of baryons is exactly factor of 5 too low, factor of 10 to 20 too low to close the universe. So basically now, modern estimation of the total contribution of baryons, because cosmology by baryons means nucleons and leptons, everything like that, is 5%. So they already were very close back then. And by the way, this is conceptual dark matter. So they show that this is precise measurement of helium. This is very, very tightly constrained by the balance of both the creation and nuclear physics, creation and annihilation of heavier elements. But they cannot agree this with observed number density in the universe. So this is, of course, just saying conceptual dark matter. Back then, there was not still convincing evidence for this. And I say that paper, a little bit continued. So in the same very paper, they realized that they may solve this problem with this matter and prediction density to solve by introducing massless, zero-mass scalar field to cosmology. I mean, scalar fields were already known by Nordstrom, for example, and he introduced action in early 20s and before, but they really consider this, and I think this is really physical cosmology at its best, because they think about the observed properties and they really think through what kind of a physical model could explain the observations and what will be this repercussion. Not only coining a model, let's assume scalar field, but let's see what this scalar field will do. And this is conceptual dark energy, more or less, because the scalar field can be also considered as a dark energy, or even conceptual inflation that came 20 years later. This is a really amazing paper. It's only 6 pages long, and I really recommend reading it. So let's go very quickly. So how this cosmology gets its freckles. So this was the very important results from 1966. But there was a prediction that there should be this radiation. But this is not the end of the story, of course. It's the beginning of the story of this microwave background radiation. So we know that this radiation comes from was emitted from something we can consider as a last scattering surface. So before the temperature of the universe and density drop below a certain value, the photons had a mean free impact so small due to Thomson scattering that the basic universe wasn't transparent. The photons would scatter with electrons and basically were tied to the baryons, basically to the hydrogen atoms. But speaking otherwise, you couldn't form neutral hydrogen atoms. But once the universe expands, of course, temperature drops down, also density drops down. At some point, the wavelength, because the photons get redshifted, of photons becomes too big to ionize the hydrogen, and this means that didn't happen, of course, instantaneously, but with some short period of time, considering the whole time scale. The universe becomes transparent, this radiation is released, and now freely moved through the whole cosmos, and this is something we observe now in our antenna, and of course, you heard this probably, this popular talk that 1% of the shot noise in your TV, no longer the case because no one uses antenna anymore, it's all digital, but in old times when you use antenna in your TV, if you would tune the TV in between the channels, 1% of these white pixels would be from cosmic microwave background radiation. That was flying for 40 millions of years just to hit your antenna and produce a flake on your TV. But we expect some fluctuation, of course, otherwise the universe will be homogeneous, there will be no observers, there will be no structures. And soon after the big discovery of CMB, Rainer Sachs and Arthur Wolff considered that there should be irregularities, but induced by the density perturbation that induce potential perturbation. So matter density irregularities affect photon energy. And this came later to be known as Sackville Effect. There are two kinds of Sackville Effect. First is so-called ordinary Sackville Effect, or I call it non-integrated Sackville Effect, that happens at the moment of emission. So at the moment when the universe becomes transparent, there are already some fluctuations. There need to be fluctuations, and the potential in this fluctuation affects the photons. And this effect gives the shift in the temperature proportional to the phi, which is a peculiar gravitational potential, divided by 3c squared. The factor of 3 is 3 times smaller than naive expectation, but it appears because the universe at this time is still dominated largely by radiation and also matter, but it grows, the universe grows as the time to the power of 2/3, which means the local clock that goes with acceleration of the universe in this potential goes also like this. So basically this effect cancels 2/3 of the gravitational redshift. That's why the effect is 3 times smaller than naive expectation that the temperature should just depend on the potential. And this happens at the moment of emission. Now these photons go through the large-scale structure, they travel through billions of light years through time-space, and they also encounters the large-scale structure of the universe, galaxy clusters, galaxies, large-scale structure web, and then you have integrated Sackville effect that can be understood as the following: the photons fall in for example, to a cluster, they gain energy, but the time in between the time the cluster also evolves because the universe grows and you have evolution of the so basically, if in the perfect symmetry, the photon should lose going out of the cluster potential, but exactly the same amount of energy as it gains. But if the cluster is moving or the potential is changing, this effect won't be exactly the same, and you will have amplification or dim amplification by voids of the photons from CMB. But these are always something we call second-order anisotropies in the CMB. This cannot explain where the structures came from in the first place. This is something we already know happened after the CMB photons were released from the plasma. So what comes next? Well, some idea about acoustic waves in the early universe. So Sakharov was among the first one to point out the importance of acoustic waves for cosmology as well, but he only considered cold matter without photons. So not very realistic solution, but to give him justice, he was among the first one. Then Pibus and Zeldovich were among the first one to consider real plasma photon fluid. And they arrive independently, as you will see very soon, at very important results, there and their co-authors. But it was all augmented by the results of Joe's special general solution found by Joe Silk a few years later, before, in 1968, that describes small-scale damping in this photon plasma fluid due to diffusion. So basically, photons have a mean free path due to Compton scattering. So whenever you have a plasma, so the baryons are trapped here by pressure. So this is under density, this is over density. But photons can basically do a random walk and diffuse out from these regions. This means that if the scales are small, comparable to the mean free path due to Compton scattering, the fluctuations will be damped because the photons will move out of the density irregularities. This is an important result that without which you cannot explain what you observe in the CMB. Now, this is the original plot from Peebles and New paper 1970, when they consider a series of acoustic waves that should be visible in the CMB. They produce some CMB fluctuations, with the first one being the most prominent one. In the same very year, Sanaev and Zeldovich obtained completely equivalent result, but it was published in the Russian, I think, Academy of Science Reports journal. It was only in Russian, so it was later, only know a little bit later to the west, on the west side than this original paper. But to give justice to Peebles and New, they were the only one at that time that actually put forward an argument that the spectrum of some fluctuations that came before this whole effect, that seeded this fluctuation that you see already oscillating here, had to be mostly scale invariant. Later, it was called Harrison-Zeldovich scale invariant spectrum. By scale invariant, I mean that every perturbation on every scale have the same power, so contribute the same. So no scale should be special. This was 11 years before inflation was going in, and this kind of a perturbation power spectrum is naturally produced by inflation hypothesis. So this was really straightforward. This is really revolutionary thinking, I think, from 1970. And now, 40 years later, we have this picture when actually the CMB anisotropies were observed. And it was already a long story about with this, how it was for many years struggle to observe these anisotropies. This is a beautiful plot shown many times in many cosmological talks. And I'm going to very quickly try to describe, to understand what's been shown here, because I think it's one of the most powerful pictures in modern cosmology we have. So here we have the temperature anisotropies power spectrum. Use spherical harmonics because you observe the whole sky. So you expand the fluctuation in the temperatures at two different points separated by some angular scale in spherical harmonics. So that's why you have a multiple moment L and some normalized power, how much fluctuation, how much variance you have at this scale. And the green line is best fit current cosmological model, and the dots are observation. So what we see here is basically the acoustic waves from the early universe as predicted by these authors already 40 years ago and explained by them as well. So first peak corresponds to compression in potential wells. Remember, you have a photon baryon fluid, there's a fluctuations. So the gravity compressed this fluid, you have a potential well, you have a first peak, is most prominent one, that's why. Then you have a rarefaction, because the pressure starts to act against the gravity and the baryons get pushed out with photons. Then you have another compression after rarefaction, so this will be a potential hill. So basically, all odd peaks are compression, and all even peaks are smaller because of the silk damping here, are rarefaction. So if you have more baryons, the deeper will be the fall measured by the first peak to the second peak, right? Because the baryons fall here. So ratio of the first to second peak can yield you the total amount of nucleon baryonic matter. And this yields, this observation yields this to be 5% of the current energy density. In contrast, the dark matter do not feel pressure. So once they fall in for the first time, they stay in the potential well. They actually enhance the potential well. So the third peak is much higher than you would expect because the dark matter stayed there. It wasn't rarefacted. So measuring the third peak and its relation to the second yields the total amount of the non-baryonic dark matter, the one that never had any pressure with photons. And this yields to be 26%. And this is amazing because this observation and this fit is more than 40 sigma statistical significance of dark matter, non-baryonic dark matter detection in the universe. And we know this now. It was already coined in 70s by the early works of amongst many other Jim Peebles. Okay, I already said something about dark matter, so let's stay at this topic for a little bit. Dark matter has a little bit longer history than CMB, of course. Already in 30s, it was argued by Fizyki, was American astronomer of Swiss origin, that if you measure the dispersion of velocity of galaxies in galaxy clusters, so one of the biggest agglomeration of mass, visible mass in the universe, you can if you assume that these systems are in the equilibrium, so basically they're not dispersing, they're gravitationally bound, you can connect the dispersion of the velocities basically to the total gravitational energy, which basically is a depth of the potential well. And it turned out that this is 25, the dispersion is so big that it corresponds to mass 25 times bigger than the observed mass of galaxies. So this is indication of some invisible mass there, that been, at least its gravitational effect. Then another very important result was from Vera Rubin that observed rotation curve of galaxies. Rotation curve is basically a measure of a function of the rotational velocity of gas or stars with respect to the galactic center as you move out from the galaxy center. So from starlight you get something like that, and now it was known for many years that it was something like this, but you can rescale. So this is what you expect from the visible disk if there will be no dark matter. But this solution can be scaled up and down a little bit. But this part can never be explained by this only disk alone because it came much later, well, thanks to Vera Rubin and her spectrograph, and I think Chris Ford as well, because it can be observed from 21 centimeters from neutral hydrogen when you can go much larger radii from the galaxy. So this is what you expect the velocity curve should look like if there's no dark matter, or just the disk and stars, and this is what you observe. And the difference, it was attributed to the dark matter. So this was observational already, the ground was prepared for some kind of a theoretical indication. But there was a very important result here that was coined in by Jeremy Ostriker and Jim Peebles. So first of all, let me also tell you that at the same time, more or less, when this dark matter was become more and more convincing, theorists on both sides of the Iron Curtain were working hard about this idea. And among the first one, the most famous results was by Jakub Zeldovich and Doroszkiewicz that did one of the first, well, it looks funny, but back then was a state of the art. Numerical simulation, this was actually of the alphanumeric printer you can see back then, and it was in Moscow, in Soviet Union, about how the structure formation could grow in the universe if it would be filled with the dark matter, but hot dark matter. Back then, there was the idea that the neutrino could have not been massless, but could have some mass, and if neutrino would have mass, it would be a perfect candidate for dark matter, because neutrino does not emit or absorb light, but it would gravitate. This is how structure should look in the universe if the universe would predominantly filled by matter in the form of massive neutrinos. At the same time, nearly, Ostriker and Peebles did a small-scale test for kind of a dark matter. They assume, let's see what happens when we try to follow the formation of the spiral galaxy. So these are particles that supposed to represent stellar component, and they always show up that it's already you're looking from above. So this is a disk of stars, as you suspect to get from the spiral rotating galaxy. And whatever they try hard with this component, they showed out that the numerical results show out that at least already after one turn, no matter what you do, there's going to be creation of a very thick bar, stellar bar inside of the galaxy. They still rotate, but whatever disk structure that would be there would be most of the energy would transfer to the bar. This would mean that there's no way that you can form spiral galaxies and thin these galaxies in the universe if this is something that whatever you start with always end up. The only thing they could find to save this, remedy this situation, is when they embedded this stellar disk in much larger static potential of dark matter halo. And this would have been cold dark matter, not hot dark matter like here. So that was important contribution that also put attention to many other theorists what supposed to do, what you can do with the different non-relativistic dark matter. So soon after came the famous Erset and Goff simulation, when they started with some completely random fluctuations and observe some clustering that's supposed to be more or less agreeing with the observation. I'm saying more or less, and this is something not very statistical, and you will see that thanks to Jim Peebles we now can say what this more or less means. So the Peebles' crucial contribution with this point comes in 1982 when he considered non-relativistic dark matter, which of course we'll consider before, but in the self-consistent fashion, he connected fluctuation in such a non-relativistic, so otherwise cold dark matter, to the anisotropies in the CMB. And he predicted if the large-scale structure we see in the galaxy surveys would be effect of the cold dark matter forming the first perturbations, you should expect fluctuation in CMB of the order of 5 times 10 to the minus 6, which were fully consistent with respect to his precision with the Kobe observation that happens 10 years later. So he kind of predicted if the universe is cold dark matter, and what we see galaxies cluster in the following way, you should expect in this primordial fluctuation, radiation fluctuation of this scale. And this was also Nobel Prize for observers in 2006 for the Kobe mission. So now, okay, understanding how the large-scale structure coupled to dark matter and to CMB fluctuation allow for this construction of these physically motivated computer models is very important, because without this connection to the initial fluctuations, you get only this picture. You don't know what to start with. You can get some gravity, you get some power spectrum, but you don't know what the kind of amplitude you could expect here. Peebles provided a self-consistent physical model. If you want to have this, and if you want to, and we knew back then that there were no 10 to minus 4 fluctuations, for example, in the CMB. So it was well known that the fluctuations are smaller than 10 to minus 4. So he provided community with the idea what to start with such a model to get some reasonable predictions. And this was later used by White, Frank, and Davis, so a year later after the paper published by Jim Peebles, to produce the following picture when they consider cold dark matter 2 variation and neutrino, so hot dark matter 3 variation of different mass of the neutrino, make a numerical simulation that predicted how galaxies should cluster in such a universe, and they already knew what's supposed to be the amplitude, more or less starting amplitude. And this is the observations from the Center for Astrophysics in Cambridge in Massachusetts, back then state-of-the-art galaxy survey. And you could clearly see it only by eye, of course, but this is not what we do science, that this picture it's not compatible with observation. This is much more compatible with observation. This wouldn't be possible without the self-consistent toolbox provided by Jim Peebles. And what I'm saying by eye, but we didn't have to do it by eye already by 80s, because there's an often forgotten contribution from 70s, but I haven't seen this contribution mentioned in any single recent articles about Jim Peebles. But from my perspective, it's a very powerful contribution, because it's not so spectacular, but has a huge impact on the community. It's the following, that Jim Peebles was among the first one, actually there was single-handed the first one, to develop, formulate, and apply a set of theoretical tools for statistical measurements and characterization of this large-scale structure, as you see in the galaxy catalogs. So namely, he developed a theory, a physically meaningful cosmological theory, in which the correlation function, position or angular correlation function of galaxies, can be connected to the excess probability with respect to the random clustering. In this, in turn, can be expressed as a power spectrum if you go to Fourier. And basically, this is a density perturbation, and you can relate the CMB physics, dark matter physics, to this, to power spectrum, to correlation functions. So basically now these are completely standard, widely used objects every day by all these great big galaxy surveys, multi-billion programs. Very two simple tools, of course also higher orders, but this complete theory was formatted by Jim Peebles in the 70s, and only because of this we could use this observation to falsify this model, because we knew the correlation function here had completely different characteristic, power law, then this one and this one were much, and basically you could do the fitting, you can do hypothesis rejection, because you have a theoretical tool that describes the clustering. So I will be slowly going to towards the end. I mean, at the end I will have to fly through the many different contributions. So now, one of the final pieces of the puzzle, I think, of one of the very big and standing out contribution comes a little bit later, still in 80s, when we can say the Peebles helped pave the way to the lambda CDM. So think about the scalar field and the lambda. So 1984, there was a very important paper by Jim Peebles, and Jim Peebles alone, single author paper, when he reintroduced forsaken cosmological constant using arguments inspired by recently coined hypothesis of cosmic inflation by Alan Guth and Alexei Starobinsky. So basically, having lambda with constant equation of state would not spoil the success of the early universe, because back then energy of the cosmological constant would be tiny. So all the CMB, primordial nucleosynthesis, successive observation will be still valid. But at the same time, at the late time, when the dark energy becomes important because it grows with the volume of the space, it would produce the missing energy needed to close up the universe. By close up, I mean the omega, total omega should be 1. And as we see, the observed omega density of matter was much smaller than 1. At the same time, it was very plausible to have the curvature vanishing, because if the universe had this inflation, naturally we would predict that you should have Euclidean geometry at large scales. But he did himself consistently included lambda in the all equations describing large-scale structure, among many others also perturbation theory. So basically, he kind of put forward or prepared all the components of the standard model of cosmology, lambda and cold dark matter, 15 years before they were actually commonly accepted by the community, but also held by observations. And this is where you can see that why lambda was actually eventually needed, because there was a Nobel Prize in Physics in 2011 from the discovery from the 1998, namely that the faraway distant supernovae, which you can use to measure the expansion history of the universe, could tell us the difference between which of the scenario we live in. And they favored strongly the accelerated scenario with the positive lambda. Basically, lambda more or less equals 70%. So basically, Peebles was already ready 20 nearly years before that discovery. Of course, there were many others, but his contributions are really completely seminal with this. So also dark energy. And not to forget, still in 80s, it's completely amazing. I always get flabbergasted when I see how many different, how great intuition this man has. He, together with Bharat Ratra, was among the first one to consider dynamical dark energy. Namely, this was the first stage. This is Occam razor. Let's just consider Einstein cosmological constant. But what if, Peebles thought, if this lambda can be generalized to the dynamical field? So now, 20 years later, we knew there was a dynamical dark energy, big field in cosmology now. Now we have another mission sent in space and also built laboratories to see if the equation of state of dark energy is consistent with the disk being constant or with changing with time evolving scalar field. It was ready, most of the work was already prepared by Peebles Ratra. I think, to my surprise, this is one of his most cited papers, Ratra Peebles, about time evolving scalar field in cosmology. It's more than nearly 4,000 citations. This just tells you how this is timely still, because the citations grew up, and it had only like 100 citations still 15 years ago. And in 15 years, it grew up to 3,000, because it's still a very fresh topic. Okay, so I'm going very close towards my summarizing slide. I would call Jim Peebles a restless and relentless cosmologist. He's still active. As I said, it would probably require 2 or 3 more seminars to really describe and give him justice. But just let me, with one of my final slides, just present you with the later, I think, important contribution he made after these 4 or 5 big contributions I named before. So in 1988, Peebles introduced a self-consistent physical model that could explain many observations without dark matter. Back then, there was still issue, what is this dark matter? I mean, there was an exotic particle. He found a fully consistent model that passes back then all observations. It was called Primordial Isocurvature Baryon model. It was only eventually falsified 5 years later thanks to the cosmic microwave background COBE explorer that observed very precisely these fluctuations. Without this observation, this model was giving the same very good predictions as different models back then. And this is amazing. Basically, okay, his model only lived for 5 years, but it's very good because it turned out to be wrong model for the universe. But it's still amazing in my eyes. In 1989, so a year later, there's paper, and I can find Polish connection with my late supervisor, Pibus, Daly, and Ryszkiewicz, used the mass and abundance of nearby clusters to show that so-called, back then also popular, biased cold dark matter model, or standard cold dark matter, was strongly disfavored. There was a model that tried to explain the structure formation without lambda, basically saying that, okay, since you cannot have the clustering agreeing with the universe being fully filled with dark matter without dark energy, we introduce this 3-parameter bias that galaxies are basically just an arbitrary function of the underlying dark matter density field. And if you observe galaxy clustering, that doesn't necessarily mean that you directly constrain the dark matter density field. You need to multiply by this bias function. Okay, and it was very strongly argued by Simon White, for example, and Joseph Staffio that this model is much better. So Pibus, Ryszkiewicz, and Daly showed that you would have to go to 50 Hubble volumes. So you would have to observe 50 universes to find enough clusters as we already observed with the 100 megaparsec around us. So that was very strong and also a beautiful argument. 1990s, with Ed Shea and Brent Tully, he introduces the variation action principle method that now is very popularly used to reconcile orbits of the local group and also farther away galaxies, which is an important test also for some dark energy models and wasn't conceived back then. 2001, Jim Peebles published the famous The Void Phenomenon paper when he points towards a puzzling emptiness of the local void. And I think, at least according to me, it's not fully satisfactorily solved problem until now. I think there have been some solutions, but they're not fully satisfactory yet. So I think this is one of the problems that can be interesting for research. 2004, with Dennis Farrar, he formulated interacting dark matter and dark energy model. An interesting and still widely researched alternative to the lambda CDM when the energy density between dark matter and dark energy can be transferred. In 2004 and 2005, he published a series of papers with Steven Gobser and Adi Nazar when they formulate scalar interacting dark matter model, later to be known as Rebel, and that had the potential to alleviate many of small-scale problems of cold dark matter. Later, it was shown that this model fosters disfavoring features in dark matter halos, and this was a subject of my PhD thesis. So I was actually very happy because Jim Peebles provided me with a PhD thesis topic. Even though the result was null, because this model turned out to not be successful, we learned a lot by just considering this extension. In late 2000s, Peebles co-PIs and contributes to the Void Galaxy Survey, so he was still actively observing and formulating and contributing to the programs, which was aimed to study galaxies in nearby voids. And finally, 2012, he coins in his latest idea, so it's only 7 years ago, about evanescent matter. So there will be a dark matter with evolving mass and fifth force large enough to aid some early assembly of isolated galaxies. So it was an interesting model going in because Jim Peebles is still convinced that the standard model cannot explain some features we observe in galaxy evolution. And he's still very, very fresh with many ideas. So we should not forget about 3 seminal textbooks by Jim Peebles: The Physical Cosmology in 1971, The Large-Scale Structure of the Universe in 1980, and The Principles of Physical Cosmology in 1993. At least the last 2 ones are still very up-to-date. I mean, this is really obsolete now because it was soon after only CMB was discovered. But these 2 textbooks are up-to-date, and I'm using them maybe not daily, but often-wise. So so to write a textbook that after 40 years is still of great value is one of the great accomplishments as well, I think. So my last slide, because I took some time. So famous Soviet-Russian physicist Lev Landau is attributed with a saying that cosmologists are often in error but seldom in doubt. And this reflected his great annoyance with so much uncertainty connected with the cosmology as a science of the universe in 50s and 60s. And I know that from the second hand because I know this quotation from both from Anatolia Klipin and Sergei Shandarin, who were basically, Shandarin actually knew personally Lev Landau when he was very, very young. So I can think it's not exaggerated that he was very reluctant. But I think that thanks to effort of many, among which Jim Peebles' contribution to me appear as the brightest, sharpest, and with the most impact, we have witnessed a paradigm change in cosmology from a speculative, I would say nearly a philosophy, to a fully grown mature and precise physical science. And the future looks ever interesting and exciting from my perspective. Thank you very much for your attention, and I'm happy to answer all questions.
Okay, thank you, Wojtek, for this very nice and interesting talk. Time for questions, I think. Please.
Just a specific comment. So in one of the papers, I think Peebles actually estimated the value of omega lambda. He got 0.3, so not quite as for supernovae, but that was years before, right?
Of course. Yes, well, I didn't have time to say justice to Harvard. He also was one of the first one to explain how galaxies could attain angular momentum from the primordial tidal torque theory, which is now commonly accepted as the starting point, and of which you know there would be no quasars, right? So there's connection with everything. So seldom we find a scholar and with such a great horizons as Jim Peebles. So I think it's Nobel Prize. Especially, it's also, I think it should give warmth to all our hearts, as being mostly theorists in this room, that even though we sometimes work with very, I'd say, sophisticated ideas, there's still always connection with the real world because we do physics, and physics can be beautiful and sometimes can be recognized and prized.
Okay, any more questions? Well, I think the talk was really exhaustive in a sense that you covered everything, so all was clear. So I think we can end a bit earlier than usual. So thank you, Wojtek, and thank you.
Thanks for having me.